Just all you are able to see my presentation?
Yeah.
Yeah. Yeah. Can I proceed? Because I am not able to see others.
Yeah, proceed.
Yeah. Okay. So first, I want to start with the code that what I cannot compute, I don't understand. This is adopted from Richard Feynman. So we are trying to run some calculations to understand what is happening and we try what's inside it's going on. So this is for basic simple calculations we'll do in this session. And for that, for today's one, these calculations are very easy. So we need to focus on the calculations. What is the input files? What are the output files? How we can run this and what information we can collect from the output files. So this is a collaborative effort from Dr. Shumon Mondal, myself, Subhankar, Subroto, and Kaushikda from computer section, and so Professor Krishna Kumar Eshar Menon. Okay. This is the Quantum ESPRESSO software. So not software, this is the web page. If you try, if give this, if you give this path, or you can get the Quantum ESPRESSO software, you will find this kind of page appearing. Things, and we will find that it is written as Quantum ESPRESSO. It is an integrated suite of open source computer codes for electronic structure calculations and materials modeling and then analysis. It is based on density functional theory. It is based on plane waves and pseudopotentials, which you try to understand all the words density functional theory, plane wave, pseudopotential one by one. Okay. This is a schematic approach how to run DFT calculations. As this is a technical session, so I'm not going into details. What is the exact procedure? I'll tell this after a few sessions. And first, we try to understand it schematically. First, what we have to do, we have to give an input file. In the input file, we need to model a system. We have to give lattice vectors. We need to give some physical approximations like LDA, GGA. We need to give some numerical approximations. What is the cutoff energy of the system? What is the K points? What is the procedure we want to run? I'll discuss it in the next few slides. So don't worry about this. Then we need to give this in the code. We need to run it. And in the computer, they will try to solve the quantum equations. We are not going into details. What is every terms of these things? We'll try to understand it later. Then after that, we'll get an output file. From the output file, we can get different physical quantities like charge density, total energy, quantum wave functions, quantum energies, which we'll use to understand what is its band structure of the system, what is the density of the state of this system, what is its band gap, what is its work function. So from the output, we'll try to find out these things. Now, okay, this is a typical input file for carbon in its diamond structure. We know the diamond structure very well. So diamond structure is a face-center cubic structure with two carbon atoms. One is at 0, 0, 0 position, one is at 0.25 to 0.25 positions. Therefore, the structure look like this, but we are not bothering about this. We are just trying to understand what is how we can give an input file to the quantum expression. So this is a typical input file. Here you can see there is from 1 to 26 number of the lines. So we need to provide this to the system to run the code. So there are different blocks which I have marked to different colors, and we'll discuss about this. What is every line says to it. So this is the website. If you click or if you give it Google, you can find a page like this. This is the input file description. Here you can see control unit, system unit, electrons, ions, everything is there. So if you click on anyone, like if you click on calculation part, then we can see a page is appearing, which is saying the calculation. You can do different type of calculations in the Quantum ESPRESSO. One is SCF, NSCF, bands, relax, and different kind of calculations. We'll do it, and we'll do the SCF calculations in this session, and then in the next session we'll do NSCF, bands, and relax calculations. So through which you can find every quantities of it, so that you can use it as a parameter of your Quantum ESPRESSO input file. Now, in this, if you return back to this block, we can find there is a control block, there is a system block, there is electrons. There you need to provide atomic species, which I want to calculate. You need to provide atomic positions and K points. Now come to the line numbers, what is saying. Let's try to understand it one by one. Line 1 says it's a control. It declares the control block, means through which the system will control what you want to do for the calculations. Now in number 2, there is a calculation. We have put it is SCF, means we tell the system that we want to do self-consistent field calculation with plain wave method. In the third line, there is a restart mode. Restart mode is saying that from where you want to do calculations. You want to do from scratch, means you want to do the calculation from the very starting point. Sometimes what happens in doing calculations, if something happens, your calculation gets stopped, then you can also start to run the calculation from where you left it. So there are different modes of restart. So we are now trying to do all the calculation from the scratch mode, because it's a safer side. It's give you safely the converse result. Now in the fourth line, there is a prefix. We need to prefix. This is the name. You can give any name, but in all the calculations, the prefix should be constant. So this prefix name will be saved in the temporary files. So if you change different prefix names with different calculations, then in a sequence of calculations, you cannot use prefix as a different name. If you use different prefix name, then your calculation will not run, because it depends, every calculation depends on earlier calculation results. Here, to trace, we are able to, through using Quantum ESPRESSO, we can calculate stress. We can calculate what is the force on the atoms through line 6. But if you don't need this, you can omit these lines. Now, in the line 7, this is the pseudo directory. This is a very important thing, that where is your pseudo potential is placed. If you don't give the input file proper pseudo directory, then the system will not run, because it will not find the location where is your pseudo potential is stored. In the next sessions, we'll we'll see that how pseudopotential is important for the calculations. Now, in the outlier, in line 8, outlier is saying where you want to store your calculator results. This path, in that path, or what path you will give, it will save your output results. Okay, in number 9, this slash sign denotes the end of your block. That means in this control unit, you are using this much of parameters for your calculation. This is not enough. There are so many parameters here. You can use every parameters, but according to your need, what you want to calculate or what you want to get an output. So depending on this, you can use parameters like this. So as we are doing simple calculations, so we have used this much of tags in the control unit. Now come to the system block. Line 10 to 13. System block is very important for a user to give the what is the atomic what is the system information to the input file. Here, first is the iBrab. iBrab gives you the crystal system information. Here I am using iBrab 2. Here, if you look at this point, here iBrab 0 means structure is free. We are not going into this. Now, if you use iBrab equal to 1, it's a cubic structure. If you are informing system that what structure is of your sample, so you are giving to this input. If you use 2, then you are saying it's a cubic structure. If you FCA, phase center cubic structure, if you give iBrab equal to 3, so then you are giving DCC structure. If it is 4, then it's a hexagonal and triangle system. And according to this, just like hexagonal system, you need to give what is the C by A ratio. So if you click on this path, then you will get the iBrab and you will get a system block. Within the system block, you can get iBrab documentary. So through which you can select what is your structure of your input file. So this is very easy. If you go to the Quantum ESPRESSO site, pw.x, in the under system block, you can get iBrab structures. All the iBrab structures are there. Okay. This is iBrab also used to, because the symmetry of the structure can be reduced to the number of calculations you need. We'll discuss a bit later of this system. Now it's a cell team. This means cell dimension. Cell dimension here I'm using cell dimension 1 is a 6.60. That means we are using it as a lattice constant. As we are using iBrab equal to 2, that means it's a phase center cubic structure. So its A, B, C are the same. So I am giving cell dimension 1 equal to 6.60. Here one should notice that this 6.60 is in Bohr unit, not in the angstrom unit, because Quantum ESPRESSO can understand this as angstrom unit. So we need to give it in the Bohr unit. Okay. Now, you can also use cell dim 2, 3, depending on the structure you are choosing in it. And in the under the iBrab section, you can get all the information of the system. After that, NAT. This is the number of atoms you are using in the Quantum ESPRESSO code. Means here you are using, let's see, under atomic positions, there are 2 carbon atoms which are at 0, 0, 0 and 0.25, 0.25, 0.25. So we need to provide number of atom equal to 2. Now is the n type, means number of type of atoms. How many types of atoms you are using in the calculation? Here, as we are using only a single carbon atom, so we have put it n type equal to 1. Now the E-cut WFC means what we are using wave function, plane wave function. So there is a cutoff energy of the system through which you are suggesting the system up to which we can calculate its energy or how much precision we want to get the output result. I'll discuss a bit what about the E-cut WFC and how we'll get this. What is the estimated value? All these are the system blocks, and there are much more in the site. You can check it and give it according to your need. Now we come to the next block, electrons block.
Purunapura,
Yeah,
in the previous slide, cell diamond in bracket 1.
1.
What this signifies by 1?
Yeah, 1. Here 1 means A0. Only A value, A, B, C. It can be 3-dimensional. So seldom 1 means only the A value. A0
If the structure is not cubic,
not
then
cubic.
if A equals to B but not equals to C, then
C.
In bracket it will be 2.
Not 2, it will be 3. If you look at this, seldom 3 equal to C by A. You cannot directly put what is the value of C. You have to put what is the value of C by A. Here, are you able to see my cursor?
Yeah.
Yeah, this is the hexagonal structure. You can put it here, seldom 3 equal to some value, which is the value of C by A.
Okay.
Yeah. If you click on iBrap, it will written very clearly what you have to use for your structures. There are lot, not 4. There are, I think, 8 or 10 things are there. Structures are there, so you can choose whatever you want.
Okay.
Yeah. Now we come to the electron block. In the electron block, there is diagonalization, there is mixing beta, mixing mode, converse threshold. So for this, we are not much bothering about this block because we'll try to understand it, what these do. This actually, what I have showed in the earlier slide, this consum equations. So a computer will try to solve these consum equations through diagonalization method, which is if you don't understand it, then you can set the system's default value. No problem. The system will do computation according to these values, and these all are actually the default values I'm using. So don't much bother about this. The system will take care of this. But later we'll try to understand what this is if you are a bit more expert about of these inputted files. But if you don't give this, the system will also run, no problem. Okay. Now we come to the atomic species. But in the under this atomic species, we have to provide 3 things. What is the atomic symbol? What is its atomic weight? And what is the pseudo potential for this corresponding atom? I'll show you how you get this pseudo potential, but for this session, I have provided the pseudo potential, so don't worry about this. But I will also show you how to get the pseudo potential for another atoms. Next is the atomic positions, as we discussed earlier. So we need to provide what is the name of the atom, then the corresponding X, Y, Z of the system. Now the K points, as we know, this is a calculation should be done in the first Brillouin zone. So we need to provide what is the amount of K points we need to consider for the calculation. If you don't know much about this, just put automatic, and in the under the automatic mode, it will calculate what is the K points distribution of the system with the format that we need to provide three numbers here: nkx, nky, nkz. Here we are putting offset value 0, 0, 0, but we can put the offset value 1, 1, 1. I'll show you what this means. But we always cannot put automatic values. K point equal to automatic. When you try to solve the band structure of the system in the next class, I'll show you, instead of automatic, we need to use a different card to get the proper path through which we need to calculate the band structure. So this is in the next session, so don't worry about this. Now we can push the K point equal to automatic value, and we need to provide three numbers here, means like 4 cross 4 cross 4. The system will calculate for this amount of K points, and we are putting offset value as 0, 0, 0. Okay. Now these are the all informations about the input parameters. So it's very easy. You can put it one by one. We can use what is the demo file we have provided. So you can change its value, and we can run different SCF calculations, and we can try to understand what is happening to the system. Before running that, just I need to give a bit more view of the system, that for this diamond structure, there is two different kind of unit cell we consider. One is the primitive unit cell, one is the conventional unit cell. So a primitive unit cell is the smallest repetitive volume in a lattice, whereas the conventional unit cell is the smallest repetitive volume that represents the global lattice. Just if we look at this is the conventional unit cell. In the conventional unit cell, if we want to draw the structure, we at least need 8 atoms. But in the primitive unit cell, we need actually 2 atoms. If we see both the structures, the output results are same, then what we observe, with increasing amount of atoms in the calculation, means here, if we increase the number of atoms here, then the calculation time also increases. So it is computationally efficient to choose the primitive unit cell. So when we run the silicon structure for this exercise, we will find that system itself choose the primitive unit cell. So if you want to run the system for this conventional unit cell, you can also do so. So it's for your exercise that to check this conventional unit cell and primitive unit cells are giving the same result. So we'll choose the primitive unit cell for this system. Now come to the pseudopotential part. What we have discussed is that under atomic species, we need to provide atom, atomic weight, pseudopotential. Now, this pseudopotential should be included in this pseudo directory. So you need to provide the pseudo directory, which I have told you that in the pseudo directory, this file should be present. Otherwise, the calculation will not run. And how many pseudopotential you need to put? Because you have to put one type of atom, so you need to put one type of pseudopotential in this pseudo directory. If your system has two different kind of atoms or three different kind of atoms, you need to put three different pseudopotentials in this system, in this directory. So here we try to understand why we need this pseudopotential. If we know when electrons is running in a periodic potential, and we know this is Coulomb potential equal to minus proportional to 1 by. As R tends to 0, then the ionic potential goes to infinite. So this is a computational problem. We can't do anything with the infinite values. So what suggestion is that we replace the strong Coulomb potential of the nucleus, and we just below a certain cutoff values, we just smooth the pseudopotential to a finite value, or the pseudo wave function to a finite value. So these all informations are contained in this pseudo file. So we don't have to do these things. We just only need to specify what is the pseudo file. Within the pseudo file, all these things are included. So we don't need to worry about this. We just need to provide the proper pseudo file. Now, where we can find the pseudo potential. So this is the path where you can find the Quantum ESPRESSO pseudo potentials, and in the pseudo potential file, this is nearly all atoms are present there. If you click on any atom, then pseudo potential of this corresponding atom will be opened up, and you can download from there and you can use it. But before using that, I just want to say that there are different kind of pseudopotentials, and in the pseudopotentials, you can find this is the PBE form of the pseudopotential, which is developed for Quantum ESPRESSO, and it is well optimized for this Quantum ESPRESSO, and the results are fine. And the type of pseudopotential is written here. This is RRKJUS. This is basically ultra soft pseudopotential, means you need a lower cutoff energy for this system. But here, one thing we always need to remember is that if we are using different atoms like Fe and cobalt, then we cannot use different type of exchange correlation function. Like in cobalt, we are using PBE, but in case of Fe, we are using PZ. But these two cannot mix up in the calculation, so output will give you an error. So either you have to use for both the system PBE or both the PZ. Means you need to give same type of exchange correlation function for the pseudopotentials. But if you are using single atom, so it will not be a serious issue. You can use these PBE, RR, KJUS pseudopotentials. This means ultrasoft pseudopotential. I think all the calculations will run properly. But if you have doubt that your pseudopotential is not working properly, then you can choose other pseudopotentials and check your results, which is more appropriate to match with the experimental values. Okay. Now we come to the plane wave expansion. We know that what we are calculating in a periodic system. From the block theorem, we know that for any potential, we can periodic potential, we can expand it through the
I think Orko have some question.
Orko, you can take. Yeah, Orko. Hi, Orko.
Orko.
Okay.
Okay, you can continue. Orko.
Yeah, you can.
Okay,
Yeah.
Orko written down his question.
Please repeat the pseudopotential part.
Yeah. Can you read the question? Actually, I'm not able to see this.
Can you please repeat this part? I think Orko want to.
Please repeat the pseudopotential part. Orko has
Okay.
asked.
Okay. Orko.
His mic is not working, or I cannot turn on my
Okay.
mic.
Yeah, I don't know which part he is asking. Orko, we can talk actually if you have problem. Yeah.
Purnavada,
Uh-huh.
Orko is telling his mic is not working.
Okay.
He has asked, please repeat the pseudopotential part.
Okay. Yeah. So to run the quantum espresso, we need to provide a pseudopotential file. Why we need to provide this? If we look at the system, when an electron is moving in a periodic potential, then it experiences a Coulombic force. So if we find what is the expression for this, this is the ionic force. This is proportional to minus of 1 by r. Now, if r tends to 0, then what will give? Ionic potential should be infinite. But we can't do any calculation with infinite values. So what to do now? Now, an solution is that it's better not to have anything, then it's better to have something. So then what we have done, not we, actually physics community has done this, that up to a certain part, there is a, you can see, this is, you can see it here, this is real potential, this is pseudo potential. So what we have done, inside the core, but nearly core, we have replaced the all electron potential by pseudo potential. You can see this is the pseudo potential. And this pseudo potential is replaced near ion existence, near ion force. The same way in the pseudo potential, pseudo wave function also, in this kind of pattern is replaced by a smooth function. What will happen is then the calculation will run in an effective way, and the amount of expansion coefficient, I'll show you for the Fourier expansion coefficient, the number of Fourier expansion coefficient will also get reduced. So both will help us to calculate the properties of the system. So this is the motivation of the pseudo potential things. So we don't need to worry about this because all these things are included in this potential file. So what we need to do, we need to just give what is the potential, pseudo potential file. If we provide this, it will consider all these things and give you a result. You don't need to do anything. You just only need to provide the pseudo potential file. And this pseudo potential file should be in the pseudo directory. Otherwise, system will not run because it will not find where is your pseudo potential. And this is the pseudo potential. Here, this is the path where you could find your pseudo potentials. If you give this path, you will find a page like this, quantum espresso pseudo potentials. And here what is your element depending on this. For example, I am say giving here on oxygen. If we click on oxygen, then it will give different kind of pseudopotentials like this. So what we need to use for this quantum espresso, you can use all of this, but for this PBE and ultrasoft pseudopotential are well optimized for this pseudo quantum espresso calculation. So we always try to use these PBE ultrasoft pseudopotentials for the calculations, but you can use others. You can try to use other pseudopotentials and try to find what is your result. If you find other pseudopotentials are giving you better result, then you have to use that pseudopotential for your system. So always you can check which pseudopotential is the best for you. Now here one question is that if you are using two different atoms like Fe and cobalt, one thing is that you cannot use two different exchange correlation functional. Like here, if you look at this, cobalt is using PBE pseudopotential, but here you put Fe as a PZ, then this will give you an error. So what you have to do, you have to use for both the case PBE pseudopotential or PZ pseudopotential. Both should be the same, so that it will, your system will run without giving any error. Okay. Now the plane wave expansion of our system. As we are trying to understand this, that when there is a periodic potential, we always try to expand the system in terms of plane waves. So if you write for the wave function for this system, we can find expansion should have, wave function should have this kind of expansion, this kind of Fourier coefficients. So we can take infinite number of expansion coefficients, but if you increase the number, then your calculation time also increases. So it's always better to take a certain amount which is useful for your calculation and also give you a desired result. Not 100% exact. If you want to do something 100% exact, then you need to increase ECART WFC to 40 to nearly 1000. But this give you a lot of computational time. It takes lot of computational time, so it will not efficient for the system to run. So what we need to do, we need to optimize what is the ECART value should be used for our calculation. So for every calculation, we need to do cutoff, energy cutoff variation to say check where is your system is converging with the ECART or not. For this, I'm just showing a thing that this is the total energy of a calculation and what we have plotted with different cutoff energy. Means we are changing this cutoff energy and we are trying to see when the system is converging with respect to the total energy. So what we find is that above 20 or you can say 30 read bar, the total energy is not changing, though we are changing the cutoff radius. So we can, but here we can check that if we are using the, if we are increasing, when we are increasing cutoff energy, the time required for the calculation is increasing. So it's not a good idea to use like ecart equal to 100 and it will take a lot of time, where some other one is using ecart equal to 30, but he's taking less amount of time, but the results are same. So you need to optimize which ecart value is appropriate for your calculation. So it need to be done every time before you run a calculation, basically an SCF calculation. So we will do this in our exercise for the silicon system. What is the cutoff energy we need to consider to calculate the system? Okay. Now coming to this K point part. What we need this, as we are calculating all the things in the first Brillouin zone, and we are calculating in the reciprocal space. The reciprocal space will look like a point when we are using a plane wave expansion of the system. Now, to calculate any quantity, we need to consider points. Here points, 1 points, 1 points. So we need to consider different points in the K space to calculate anything of the output as a output quantities. Here we are considering 4 cross 4 cross 4, means we are taking 4 into 4 into 4. Of K points in the Brillouin zone to calculate the 4 amount of K points. But what system will do, because the system will reduce the number of K points according to the symmetry of the system. Like you can see here is a square pattern. But you can take as a 4 cross 4 unit cell, 4 sorry, units, not unit cell, K points, 4 cross 4 K points. But look it here. If you reduce it to the system through symmetry, you can see these 3 points are good enough to represent your system. So why you want to take then more? Obviously, the system will reduce the amount of K points. So you don't need to worry about that. What could be the reduced K points? The system itself will do this, but we have to just provide what is the number initially you want to put in. If you can put 2 cross 2 cross 2, if you can put 4 cross 4 cross 4, 6 cross 6 cross 6, 8 cross 8 cross 8, whatever you want to do. But as the number of K points increases, the amount of computational time also increases. So here we also need to compromise. What could be the total energy convergence and what could be the time? So if I show this, you can see it here. Here 2 graphs. One is no offset. No offset means this 0 0 0, and offset means 1 1 1. So you can try to put both 0 0 0 and 1 1 1. What we have done? We have done 1 cross 1 cross 1, 2 cross 2 cross 2, 4 cross 4 cross 4, and continue to 10 cross 10 cross 10. What we observe is that after this, you can say this 6 cross 6 cross 6. After these values, no total energy getting changed if we increase the K points. But if we increase the K points, the amount of time is increasing. So if you take 10 cross 10 cross 10, it will not give you more benefit, but it will take more amount of time. So why to do with 10 cross 10 cross 10? Then we can perform the calculation with 6 cross 6 cross 6. it will give the same result of the total energy. So here also we need to optimize in every cases what K points we need to take for our calculation. So in the exercise, we will check for the silicon case what amount of K points we need to consider to stabilize or to get a convergent value of the total energy of the system. Okay. Now we come to a part that we also want to obtain what is the lattice constant of this system. So what we can do, we can find the total energy of the system with different lattice parameters. That means if I can say this is the cell dimension, so we can change the cell dimension and we can find what is the
Shubhankar has asked one question.
Yes.
What are these K point offset values?
Yeah. Just one thing is that if you are this is your first Brillouin zone, you are trying to divide your K space with number of points. That means you are taking 4 cross 4 cross 4. So K points would be like this. But if you point this B center of the K point here is no K point. Means here you are not offsetting your K point values. If you offset your values to 1, 1, 1, then the center of this point will go shift to another position, this point. So depending on the symmetry of the system, sometimes offset values can also give you less number of K points, which reduces your computational time. Not much. It will not going to change your computational result. Just it only give to change what is the number of K points will be used in your calculation. If you see with 0, 0, 0 points, 10 number of K points are used in your calculation. If you offset these values, if you will find the number of K points needed is 5, then obviously your calculation time will be reduced. But if you find after offsetting the amount of K points needed to 20, then obviously your K calculation time will increases. So it will not giving you much in your computational results, just to check where your symmetry is. Okay. Here you can find is that with offset the time required is getting up more than this no offset values. But here you can find total energy after these 6 cross 6 cross 6 K points are not different. So here will be more efficient to use a non-offset value, means 0, 0, 0 value for the calculation, because it will reduce the time of your computation. Okay, just now I'm trying to understand what is the lattice constant optimized. Okay, so what we have to do, you have to change the lattice parameter. What I have showed you earlier is that you can change the cell dimension one value, like here it is 6.6, you can use 6.4, 6.2, yeah, 5.8, and you can check what is the total energy of the system. And if you found a this kind of shape. Where is the minimum position? This minimum position is basically your optimized lattice constant for the calculation. So you can use this for your calculation. So, but here you can use some conversion. Means it is in the Bohr unit, but here it is plotting as angstrom unit. So you can change it very easily. Through which you can find what is the optimized lattice constant. So after optimizing the lattice constant, K values, cutoff values, we can proceed for the calculation, final calculations. Okay. Now have a look. What is the input file? I have given you already an input file. This is the control unit. This is the input file for silicon. This is the cell dimension. I am using SCA here. I need to start from the very beginning. I have used silicon as prefix. My out directory is temp, means under this temp directory, my output files will be stored. This is the pseudo directory where I have put it my pseudo potential, means this silicon pb rrjkjus file. I have put it in pseudo. I have chosen it ibrap equal to 2, cell dimension 1 equal to 10.26 with the experimental parameter, and number of atom 2, number of type 1. In band, here I am putting extra band to calculate the highest and lowest and highest occupied band structure. This is mainly used for band structure calculation. We will discuss it bit more during band structure calculation. I am using ECART WFC 40 and ECART rho equal to 400. Here, just I have omitted diagonalization procedure. You can omit this also, no problem. Put it silicon, its atomic weight. I put it 2 positions here, 0, 0, 0, 0.25, 0.25, 0.25. I put it 6, 6, 6, and no offset values. So, in the earlier video, I think you have already learned it, how to upload change parameters to these things, and you can check parameters according to your convenience, according to the exercise, and you can read your output file, and before doing any calculation you can pick up your needed information from the output files. Now have a look of the output files. What is the output files? Are you able to see my output files? Yeah?
Yes, Arunavada.
Yes. Okay, this is a typical output file. The first line is showing it's a 7.0 version we are running through. We are using single processor for the running, and it is using one node. So it's using one node. Here it is showing ibrap 2 lattice parameter what I have used. It calculated volume and how many number of electrons it is using is showing here. Number of states, wave function states is also saying here. And if you go down, so iteration after this calculation started. This is the iteration. So if you go down, and here is the important parameter. This is the mark where you can find total energy of the system. You can put it down, write it down for your further graph plotting. Here is the highest and lowest occupied level of the system. Here is the number of iterations needed for the convergence test. You can find in the output file. Output file output data file are saved in this directory, and this is the basically the time through which it is required for your calculations. So you can write down all this information from your output file, and you can plot this. You can plot this further, which I have showed you. So just last slides, nearly last slides. Yeah. So now if we have a look, we have given input file as a text file, .in file we have provided. We have done pw.x calculation. We have found what is the output files. For that, we have done up to that point. Now, in the next session, what we will do, from this output file, we can get out what is the data. And from the data, we can do post-processing for band structure, density of state calculations, which we can do through GNU plot, origin, this folder. So we'll discuss about this in the next session. And in the next session, we'll do band calculation. We try to find what is the high symmetry directions of a system. We will do density of state calculation. We will do NSCF calculations to find the band structure density of states of the system. And in this exercise 1, you will find how to do equation of state. It is nothing but the equilibrium lattice constant calculation of a system. So we'll do these things in the next session. I think we'll do this in 14th. If you are interested, obviously. Okay, thank you for your attention and enjoy the exercise 1. I've already sent the exercise. So just do it and you can send me the results. Thank you.
Ornavoda, thank you for this great presentation.
Yeah, you just
if anybody has any question, they can ask.
Yeah, can ask. They can do the exercise. Actually, exercise is very important.
Yeah.
So you
Afsar is